It's not a comet. It's not a meteor shower. It's not space debris falling out of a decaying orbit. It is a solid piece of rock, roughly 340 meters across, older than the Earth's oceans. And on Friday, the 13th of April 2029, it will pass beneath the ring of satellites that carry your television signal, your weather forecasts, and your long-distance phone calls. Its name is 99942 Apophis, and the part that unsettles the people who study it is not that it comes close. It is that it comes close on a date we already know, to a precision measured in minutes, and there is nothing anyone will do about it except watch. Because here is the twist. We are not tracking this object to stop it. We are tracking it because it is the closest thing to a controlled experiment that planetary science has ever been handed. A body of this size passes this close roughly once every 7,500 years, according to estimates published by NASA's Jet Propulsion Laboratory. Nobody alive will see another. Every major space agency on Earth has quietly reorganized part of its schedule around a single afternoon in 2029, and 2 spacecraft are already being prepared to meet it. Today, we break down everything. What Apophis is, where it came from, why it terrified astronomers for 7 years, what will actually happen when it arrives, and what comes after. No filler, just the facts. Start with the discovery, because the discovery is where the fear begins. On the 19th of June, 2004, 3 astronomers working at the Kitt Peak National Observatory in Arizona, Roy Tucker, David Tholen, and Fabrizio Bernardi, picked up a faint moving point of light against the fixed stars. They tracked it for 2 nights. Then weather closed in, the object slid into an awkward part of the sky, and it was lost. This happens constantly. Most near-Earth objects are found, briefly observed, and then vanish into the statistical noise until someone recovers them years later. Apophis was recovered in December of the same year by observers in Australia, and when the new observations were combined with the June data, the orbit solution changed. Not slightly. The object was not drifting harmlessly through the inner solar system. It was crossing Earth's orbital path, and the uncertainty region, the volume of space where it might actually be on a given future date, included our planet. On the 27th of December 2004, the calculated probability that Apophis would strike the Earth on the 13th of April 2029 reached approximately 2.7%. That is roughly 1 chance in 37. It was rated level 4 on the Torino Impact Hazard Scale, a 10-point scale used to communicate impact risk to the public. No object before or since has ever been rated that high. Level 4 is defined as a close encounter meriting attention by astronomers, with a 1% or greater chance of a collision capable of regional devastation. Understand what 1 in 37 means. It is not a remote possibility. It is worse odds than most people accept when they board an aircraft, by a factor of many millions. For a period of days, a small number of specialists at JPL and at the Minor Planet Center were looking at a number that said a 300-meter object had a measurable chance of hitting an inhabited planet within a single human lifetime. The mechanism behind that uncertainty is simple, and it is worth understanding, because it explains almost everything about how asteroid tracking works. When you observe a moving object in the sky, you are not measuring its position in 3 dimensions. You are measuring its position on a 2-dimensional surface, the sky as projected from Earth, at a series of moments in time. Distance along the line of sight is inferred, not seen. From a short arc of observations, many different orbits fit the data equally well. Those orbits diverge slowly at first, then dramatically as you project them forward. The result is not a point prediction. It is an uncertainty ellipse, a smear of possible future positions. In December 2004, the Earth sat inside that smear. The smear shrinks with more data. Every additional observation constrains the solution, and in early January 2005, the constraint arrived from an unexpected direction, the past. Researchers went back through archived images taken by the Spacewatch survey in March 2004, months before the official discovery, and found Apophis sitting there, unremarked, in old data. That extended the observation arc backwards by 3 months. The orbit solution tightened. The 2029 impact probability collapsed to effectively 0, but it did not end there, and this is the part most retellings skip. Ruling out 2029 did not rule out Apophis. Because of what happens during the 2029 flyby itself. When an asteroid passes close to a planet, the planet's gravity bends its path. The closer the pass, the sharper the bend. Apophis will pass close enough that Earth's gravity will substantially rewrite its orbit, changing its period, its shape, and its classification. Before 2029, Apophis is an Aten-class asteroid, meaning its orbit is mostly inside Earth's. After 2029, it becomes an Apollo-class asteroid, spending most of its time outside Earth's orbit. One afternoon, and the object is permanently reassigned to a different family. That rewriting introduces a problem. Within the narrow window through which Apophis passes, there exist even narrower regions, a few hundred meters wide in some cases, where the gravitational deflection is exactly right to place the asteroid on a return trajectory that intersects Earth on a specific later date. These are called gravitational keyholes. The term was introduced by the astronomer Paul Chodas. A keyhole is not a physical thing. It is a region of space defined entirely by consequence. Pass through it, and you come back. Miss it by a kilometer, and you never do. For years, two keyholes dominated the discussion. One would have produced an impact in 2036, another much smaller in 2068. Neither could be excluded, because the precision required to say whether Apophis would thread a 600-meter-wide region 14 years in advance was beyond what optical telescopes could provide. The answer came from radar. In March 2021, Apophis made a distant pass of Earth, around 17 million kilometers, roughly 44 times the Earth-Moon distance. Astronomers used the Goldstone Solar System radar in California, working with the Green Bank Telescope in West Virginia, to bounce radio waves off the asteroid and measure the return. Radar does something optical astronomy cannot. It measures range directly, and it measures line-of-sight velocity directly, with extraordinary precision. A single good radar pass can be worth years of optical tracking. Those observations refined the orbit to the point where NASA announced that Apophis poses no impact risk to Earth for at least 100 years. The 2068 keyhole was excluded. The object was formally removed from the Sentry Risk Table, the automated list of near-Earth objects with non-zero impact probability. After 17 years, the file was closed. There is a complication in that 100-year guarantee that deserves stating, because it is the reason astronomers say at least 100 years, rather than forever. Asteroid orbits are not governed by gravity alone. Sunlight matters. The mechanism is simple. An asteroid absorbs sunlight on its day side and re-radiates that energy as heat. Because the body rotates, the hottest region is not the point directly facing the sun. It lags, the same way the warmest part of an afternoon comes after noon. Heat leaving a surface carries momentum. The result is a tiny, continuous, asymmetric thrust. This is the Yarkovsky effect, named after the Polish-Russian engineer who described it in the early 20th century. The force is absurdly small. It would not move a coin on a table. But it acts constantly, for millions of years, on a body with no friction to oppose it, and over decades, it displaces an asteroid's position by distances that matter, kilometers, then thousands of kilometers. For Apophis, the Yarkovsky drift has been measured, and it is already folded into the current orbit solution. That is part of why the 2068 keyhole could be excluded with confidence. But the Yarkovsky effect depends on the asteroid's shape, its surface composition, its thermal properties, and above all, its spin state. Change the spin, and you change the drift. Which brings us back to the 2029 flyby. Because if tidal stress alters how Apophis tumbles, it alters how sunlight pushes it, and the long-term orbit prediction has to be recomputed from scratch afterwards. The encounter does not just test our models of asteroid interiors. It resets part of the calculation that tells us where this object will be in the 22nd century. So what is left is not a threat. What is left is an appointment. Consider what the object actually is, because the numbers matter, and most people carry a badly wrong picture in their heads. Radar imaging and thermal observations indicate Apophis is roughly 340 meters in its longest dimension, with some estimates running closer to 370. It is not spherical. Radar returns, and light curve analysis suggest an elongated, bilobed shape, something closer to a peanut than a ball, a form common among small asteroids that have been battered and reassembled over billions of years. Its mass is estimated at around 27 billion kilograms, though that figure carries meaningful uncertainty because it depends on assumptions about internal density and porosity. Spectral observations classify it as an SQ type, a stony asteroid, silicate-rich, similar in composition to the most common class of meteorites found on Earth, the ordinary chondrites. This is not an iron body. It is not a loose snowball of ice. It is rock, probably fractured, possibly held together as much by friction and weak cohesion as by its own negligible gravity. Its rotation is strange. Apophis does not spin cleanly about a single axis. It tumbles, in what astronomers call a non-principal axis rotation state, with a period of roughly 30.6 hours around one axis and about 27.5 hours around another. Picture a badly thrown American football that never settles. That tumbling is itself a clue. It suggests the object suffered a collision or a close planetary encounter in the geologically recent past, because tumbling states damp out over time. Now the encounter itself. On the 13th of April, 2029, Apophis will pass approximately 31,600 kilometers above the Earth's surface. Closest approach occurs in the early evening, universal time. The relative velocity at that moment is close to 7.4 kilometers per second, roughly 27,000 kilometers per hour. That distance number is meaningless until you anchor it. The Moon orbits at an average of 384,000 kilometers. Apophis will pass at about 1/12 of that. The International Space Station orbits at roughly 400 kilometers, so the asteroid stays far above it. But between those two extremes sits the number that gives this event its name. Geostationary orbit lies at 35,786 kilometers above the equator. At that precise altitude, and only at that altitude, a satellite's orbital period equals one sidereal day, so it appears to hang motionless over a fixed point on the ground. That property is why the geostationary belt is the most commercially valuable ring of space in existence. Direct broadcast television, a large share of weather monitoring, maritime and aviation communications, military early warning systems, an enormous fraction of orbital infrastructure is parked in that single narrow band. Estimates of the number of operational satellites there run to several hundred, with many more derelict objects drifting in graveyard orbits just above it. Apophis passes roughly 4,000 kilometers beneath that ring. It is worth being precise about the risk this actually poses, because it is routinely exaggerated. The geostationary belt is enormous, a circle with a circumference of more than 260,000 kilometers. The satellites in it are separated by hundreds of kilometers. Apophis is a single object a third of a kilometer wide, passing below the belt rather than through it, on a trajectory known years in advance. The probability of a collision with an operational satellite is extremely low. The probability that it is worth planning for is not zero, and agencies are modeling it, but nobody serious expects a strike. What the geometry actually means is different and more interesting. It means the asteroid enters the region of space that humanity has industrialized. It means that for the first time, an object this size will pass through the volume where our machines live, not merely through the abstract distance of deep space. That is a psychological threshold, as much as a physical one, and it will be visible. This is the detail that will define the public memory of 2029. Apophis is expected to reach an apparent magnitude of around 3.1 at its brightest, comparable to a moderately bright star, well within naked eye range under a reasonably dark sky. It will not look like a rock. At that distance, it remains a point of light, unresolved by the human eye. But it will move, fast enough that its motion against the background stars will be obvious in real time, crossing a span of sky in minutes rather than hours. The visibility path favors Europe, Africa, and Western Asia. Current projections have the asteroid becoming visible over the southern hemisphere, tracking north and east across Africa, and crossing over Europe near the time of closest approach. Something in the region of 2 billion people will be positioned to see it without any equipment at all, weather permitting. If those projections hold, it will be the most widely witnessed astronomical event involving a solid body in recorded history. Now the science, because this is where the flyby stops being a spectacle and becomes an experiment. When Apophis passes within 32,000 kilometers of Earth, it will experience tidal forces. The side facing Earth is pulled marginally harder than the side facing away, and that differential stretches the body. For a solid monolith of steel, this would be irrelevant. For a fractured pile of rock with weak internal cohesion, which is what many small asteroids are believed to be, it may not be. Modeling work, including studies led by researchers such as Richard Binzel and colleagues working on Apophis in counter science, suggests the flyby could induce measurable changes on the asteroid's surface. Possible effects include landslides on slopes, the shifting or reorientation of loose boulders, seismic shaking that exposes fresh subsurface material, and a change in the object's tumbling state. Some models predict a significant alteration in spin. Others predict effects too small to detect. That disagreement is precisely why the observation matters. The flyby is a test that distinguishes between competing models of asteroid interiors. This is a genuinely rare opportunity. Everything we know about the interior structure of small asteroids is inferred indirectly, from density estimates, from crater morphology, from the behavior of the few bodies spacecraft have touched. In 2029, nature applies a controlled stress to a known object, and we can watch the response. There is no other way to run that experiment. You cannot squeeze an asteroid on demand, which is why there will be spacecraft waiting. The first is already in flight. NASA's OSIRIS-REx mission collected a sample from asteroid Bennu and delivered that sample to Earth in a return capsule in September 2023. The spacecraft itself did not land. It performed a divert maneuver and continued on, still carrying fuel and functioning instruments. NASA reassigned it to a new target and renamed it OSIRIS-APEX, the APEX standing for Apophis Explorer. It is scheduled to arrive at Apophis shortly after the 2029 close approach and enter into close proximity operations, mapping the surface in detail. The mission plan includes a maneuver that deserves attention. The spacecraft is expected to descend close to the surface and fire its thrusters downward, blowing away the loose upper layer of regolith to expose what lies beneath. This is not sample collection. It is deliberate disturbance, used as a probe of subsurface structure. It is a technique OSIRIS-REx effectively demonstrated at Bennu, where the sampling arm sank into the surface far more easily than engineers anticipated, revealing that the asteroid was far less densely packed than models had predicted. The second mission is European. The European Space Agency has been developing a concept called RAMSES, the Rapid Apophis Mission for Space Safety. The intent is fundamentally different from OSIRIS-APEX. RAMSES would arrive before the flyby, not after, and observe the asteroid through the encounter, measuring its properties on both sides of the event. Only by seeing the before state can you rigorously establish what the flyby changed. ESA approved preparatory work on the mission in late 2024, with full funding decisions tied to subsequent ministerial-level budget rounds. Whether the mission flies depends on schedule and money, and the schedule is unforgiving. There is no launch window extension. The asteroid does not wait. Other agencies, including JAXA and organizations in South Korea, have studied Apophis mission concepts of varying maturity. Some may fly, some will not. That should be stated as uncertain, because it is. Step back and consider why any of this receives funding, because the answer is not curiosity alone. Planetary defense became an operational discipline rather than a theoretical one on the 26th of September, 2022. On that date, NASA's DART spacecraft, the Double Asteroid Redirection Test, deliberately struck Dimorphos, a small moonlet, orbiting the asteroid Didymos, at roughly 6 kilometers per second. The objective was to change Dimorphos's orbital period around its parent body by a measurable amount. Pre-impact predictions suggested a change of around 10 minutes might be achievable, with a threshold of 73 seconds set as the minimum for mission success. The measured result was a reduction of approximately 32 minutes. The deflection substantially exceeded expectations, largely because the impact ejected a large plume of material, and that ejecta produced additional recoil thrust beyond the momentum of the spacecraft itself. Deflection works. It works better than modeled. That single data point transformed the field. But DART also exposed the limiting factor. The efficiency of a kinetic impactor depends heavily on the target's internal structure. A dense, solid body responds one way. A loosely bound rubble pile responds another, absorbing energy differently and throwing off ejecta differently. To predict a deflection, you must know what the asteroid is made of and how it is held together. And that is exactly the knowledge gap Apophis in 2029 is positioned to fill, with a body large enough to matter, at a distance close enough to study in detail, with a natural stress test built into the encounter. Now, the scenario nobody enjoys stating plainly, but which belongs in any honest account of this object. Apophis will not hit Earth. That is established for at least the next century. But between 2004 and 2021, that outcome could not be excluded, and the impact was modeled. so the numbers exist. An impact by a body of Apophis's mass at typical encounter velocity would release energy in the range of 11 to 1200 megatons of TNT equivalent. Individual estimates vary with assumed density and impact angle and should be treated as approximate rather than exact. For comparison, the largest nuclear device ever detonated, the Soviet Tsar Bomba tested in 1961, yielded roughly 50 megatons. The Apophis figure is on the order of 20 times that, delivered in a single instantaneous release. The Tunguska event of 1908, which flattened an estimated 2,000 square kilometers of Siberian forest, is generally attributed to an object perhaps 50 to 60 meters across, releasing energy in the range of 10 to 15 megatons. Apophis is around 6 times wider, which means it contains something in the region of 200 times more material. It would not detonate in the atmosphere the way a smaller stony body does. At that mass, it reaches the ground. A land impact would excavate a crater several kilometers across and destroy structures across a region hundreds of kilometers wide through blast, thermal radiation, and seismic effects. An ocean impact would generate tsunami. The regional devastation would be historically unprecedented, but it is important to be accurate about the ceiling as well as the floor. This is not an extinction-level event. The impactor associated with the Cretaceous-Paleogene extinction 66 million years ago is estimated at 10 to 15 kilometers in diameter, something on the order of 30 to 40 times wider than Apophis, and tens of thousands of times more massive in energy terms. Apophis is a civilization-scarring object, not a civilization-ending one. That distinction is not comfort, it is calibration. And calibration is the point, because Apophis is not rare. NASA's near-Earth object surveys have cataloged well over 30,000 near-Earth asteroids, with new discoveries added continuously. Surveys are estimated to have found the large majority of objects 1 kilometer and above, the genuinely global threats. The completeness fraction drops sharply as size decreases. For objects in the 140-meter range and above, the size threshold defined for regional devastation, a substantial fraction remain undiscovered. Estimates of that fraction vary between studies and should be treated as uncertain, but no serious survey astronomer claims the catalog is complete. The implication is direct. Apophis was found in 2004 and then lost within days. It was only recovered because someone was looking, and only characterized because archived images happened to contain it. Objects of comparable size pass Earth without warning. In February 2013, an object roughly 20 meters across entered the atmosphere over Chelyabinsk, Russia. It was not detected in advance. The airburst released energy equivalent to roughly 400 to 500 kilotons, shattered windows across the city, and injured over 1,000 people, almost entirely from flying glass. It arrived from the direction of the sun, in the blind spot that ground-based optical surveys cannot cover. That blind spot is being addressed. NASA's NEO Surveyor, an infrared space telescope designed specifically to find near-Earth objects, including those approaching from sunward directions that optical telescopes cannot see, is in development, with launch targeted for the late 2020s. Infrared is the correct tool because it detects heat rather than reflected light, so a dark asteroid is no longer effectively invisible. Schedules for major space missions slip routinely, and this one has already been affected by budget cycles, so treat any specific launch date as provisional. There is also a practical dimension that rarely gets discussed. Satellite operators in geostationary orbit will be given an approach forecast years in advance, and the standard response to any conjunction warning is a small avoidance maneuver, a burn of a few centimeters per second, costing fuel that directly shortens a satellite's operational lifetime. Whether any operator judges the risk high enough to spend that fuel is a commercial decision, not a scientific one, and it will be made on the basis of tracking data refined in the final months before the encounter. It is a small illustration of something larger. Near-Earth objects have quietly become an operational concern for an industry that did not exist when Apophis was formed. Return to April 2029 and consider what the day will actually look like from the ground. There will be no sound, no shockwave, no detectable gravitational effect on your body, your building, or the tides. The asteroid's mass, though enormous by human standards, is utterly trivial on planetary scales. Its gravitational influence on Earth at 32,000 kilometers is smaller than the influence of a nearby mountain range. Earth will not be perturbed, the asteroid will be. That asymmetry is the whole story. This encounter changes Apophis permanently and changes Earth not at all. What you will see, if you are in the right hemisphere with clear skies, is a star that is in the wrong place, moving in the wrong way. It will rise or appear, track across the sky, at a rate you can perceive with unaided vision, and pass on. It will take a matter of hours from first visibility to fade. Most people who see it will not fully register what they are looking at. What will be happening, in that same window, is a coordinated observation campaign, unlike anything attempted for a small body. Radar facilities will attempt high-resolution imaging capable of resolving surface features meters across. Optical observatories worldwide will track the light curve continuously to detect any change in the tumbling state. Spacecraft, if present, will image the surface before, during, and after. Every one of those measurements is a data point in a question that matters. What are these objects actually made of? And what would it take to move one? Because that is the sentence underneath all of this. Apophis is safe. The next one might not be. And the entire value of 2029 lies in what it teaches us before the next one arrives without an appointment. There is a final detail worth stating about the name. The object was designated 99942 and initially known by the provisional label 2004 MN4. When the discoverers earned naming rights, they chose Apophis, the Greek rendering of Apep, the serpent of ancient Egyptian mythology that dwelt in darkness and sought each night to swallow the sun. Ra, the sun god, fought it off before every dawn. The name was chosen partly as a reference to a television series the discoverers followed, and partly because it was, by their own account, fitting for an object that had briefly threatened the Earth. It is one of the very few asteroid names that reads as a warning rather than a dedication. Whether that reads as poetry or as astronomers with a sense of humor is a matter of taste. What is not a matter of taste is the schedule. The 13th of April, 2029. 31,600 kilometers. Beneath the satellites, above the atmosphere, visible to 2 billion people, studied by 2 spacecraft, and then gone, on a rewritten orbit, into a solar system that has no interest in our timetables. The one thing to take from all of this: Apophis is not a threat. It is a rehearsal. Everything humanity learns in April 2029 about what asteroids are made of and how they respond to force is knowledge we will need for an object we have not yet found. The value of this flyby is entirely in what it prepares us for. Subscribe. We track this as it develops. Mission approvals, orbital refinements, launch windows, and every observation campaign between now and the encounter. Next, we break down the object that arrived with no warning at all, Chelyabinsk, 2013, and the sunward blind spot that still exists today. No guessing, just the facts.